All right, good evening, everybody, and welcome to this session on data structures and algorithms. We are discussing dynamic programming, and this is session number one. Technically, it is supposed to be session number two, but I had to cancel the last class, so this is session number one. And dynamic programming, I'm going to cover in multiple sessions, and now at least 3 sessions, including this one. And I hope that everybody gets a good understanding of the topic. It's a pretty important topic, both in university level courses and programming interviews. And it's a kind of a hard topic, I would say. And even I find myself like uh, pretty troubled by it, hard dynamic programming problems. So what I'm going to do is, as usual, I'm going to take some examples and then explain what dynamic programming is, why do we really need it, and instead of going the theory way and then solving the problems, I'm going to take the problems first, and then uh, as we understand the need for dynamic programming, I'll explain the theory as we move along. So just I'm going to keep a document open for the notes. The main thing that we want to cover from all of this is dynamic programming. Short, we call it DP. So the main thing that we want to get out of this is what is DP. Then why DP? Why is it needed? Then what type of problems are good candidates for DP? At the end of this talk, I hope that everybody is able to understand the pattern of the different patterns with which we approach a DP problem. And then you're able to apply those patterns to solve the problem. And you're able to recognize that a particular problem can be solved using DP. There are some technical terms that will be involved. As I said, I will cover them when I move forward in the course. So what is top down versus bottom up business? What when people talk about DP, they talk about top down, bottom up. What is that? And which one is easy and which one is hard, or whatever. It depends on person to person. Some people approach one way, some people approach other way. And I will keep adding to these notes. So let's go to DP with a very basic problem, right? Let's begin the problem of Fibonacci numbers. This problem as such is also asked sometimes in interviews, and but it's a pretty simple problem, I would say. So what is a Fibonacci number problem? So basically you have to construct a number in a Fibonacci sequence. A Fibonacci sequence is basically a sequence that begins with two numbers, 0 and then 1. And then followed by that, every single number is the sum of the previous two numbers. So the third number is 1, and the fourth number is 2, and then 3 and 5, and so on. So that's a Fibonacci sequence. The usual problem is, given a number, write a function, whatever you want to call it, let's say fib, and then given a number n, generate the nth Fibonacci sequence. So it's a pretty common problem. Everybody in computer science does it in the very basic recursion course. But through this, I want to give you an understanding of what DP is and why it's useful. And then we're going to cover one more problem, which some people may say it's not a DP problem, but it is. And we're going to see DP from a different perspective in that problem. So constructing the Fibonacci sequence, right, in this way. Let me write a very basic piece of code for this. I'm just going to fire up my IDP and write a very simple piece of code. Just go to, I'm just going to call it fib dot py. Just increasing the font a bit. So I'm going to write using Python. If you're not familiar, that's fine, because basically the syntax is going to be really simple. I'm just going to define a function fib of n. And when I'm writing recursive code, I hope everybody understands at least the Fibonacci code, but I'm still going to explain a bit. So Fibonacci, we are writing recursive code. When we write recursive code, we have to put a base condition. The base condition in Fibonacci is going to be that the very first two digits are 0 and 1. So if basically n is 0 or n is 1, then just return n. If that is not the case, then return fib of n minus 1 plus fib of n minus 2. That's about it. That's the Fibonacci code. So we are recursively calling the function on itself with a -1 and -2 arguments, because each number in Fibonacci is the sum of previous two numbers. So fib of 2 will be fib of this 0, 1, 2, 3, whatever. Fib of 2 is fib of 1 and 2. Let's make sure that this is working fine. I'm just going to call fib of, let's say, 5. And let's say, whatever, 8. Let's run this code. And the answer is 5 and 21. Seems to be working. Now, let's come to the time and space complexity of this particular piece of code. For this code, I mean, as we covered in the recursion class, there are different ways in which you can compute the time and space complexity, but I'm going to show you the most obvious way of doing it. What is happening is, in this recursive code, let's say I look for Fibonacci of 5. Then essentially, 5 is not equals to 0, not equals to 1, so we end up calling two functions, which is Fibonacci of 4 and Fibonacci of 3. I'm writing it in this sequence, but it is not called in this sequence. First, this depth will be explode, computed, and then the program will move towards here. All right, I'm going to need more space, so I'm going to just wipe this. Let's cover the Fibonacci of 5 again. Okay, don't worry about this syntax because it's too much, so I'm just going to use 5 for now. In order to compute the Fibonacci of 5, we need the Fibonacci of 4 and 3. Now, in order to compute the Fibonacci of 4 as per our code, we will need Fibonacci of 3 and 2 computed. In order to do this, we will need 2 and 1 computed. In order to do we will need 1 and 0 computed. 1 and 0 are the base condition of our recursion, so there's no further computation needed, and we can just return the answer back. Similarly, in this case, this is 1, this is okay. Then this basically again is 1 and 0. Then you have 2 and 1, then basically 1 and 0. And these many computations will have to happen in order to evaluate the Fibonacci of 5. Now, look at the space and time and space complexity for this particular code. All right, let's look at the time complexity. Each function call is resulting in 2 more function calls. So that is a very binary tree type of structure. So each parent has 2 child. So if there is one parent, there's 2 child here. Then on the next step, there are 2 square child. Then you have 2 to the power cube child. Roughly, I would say. Not in this case, right? Because this one is not expanded. It's not a real tree in this sense. It's not a real binary tree like this. It is somewhat of this type. But you can definitely say that it has an upper bound of 2 to the power n. It is slightly lower, It is lower than that, I mean, but it is definitely exponential time complexity. But one can ask question, why is that the case? This problem doesn't seem to be that complicated, right? In order to, if I was to compute the series from 0 to 5, I could do it in 5 operations. Why is this taking 2 to the power n time, this recursive code here? This recursive code sure does look concise and looks beautiful and intuitive, but the time complexity is huge. And the answer lies in the recomputation of the same problem again and again, right? So we evaluated the Fibonacci of 2 at this point. Then we evaluated it again here. Then we did it again here. For 3, we evaluated here, and then we evaluated it again here. Right? So this type of situation where a problem can be broken down into subproblems, and there's a huge overlap in the subproblems, are the ideal candidates for dynamic programming. Right? Because we are evaluating 3 here, here. So why do we need it 2 times? There's no need. Once we find out a result for 2, why don't we just store it in some cache somewhere? Let's say we keep a cache of some numbers and we say Fibonacci of 2 from now on we know is whatever 2. Right? So Fibonacci of what, 0, 1, 1, and then is also 1. Actually, I'm sorry, it's 1. Yeah, that's why I was a little confused. So we can just store it. And then Fibonacci of 3 is 2. We can just store that information forever. So when we store it in a cache, let's say like some kind of a dictionary or something like that, then when we look for, we want to evaluate the 3 again, then instead of computing this whole subtree here, we can just look at this cache in a O1 time, in a constant time, and get the answer back. That reduces the complexity of the code. So dynamic programming, let's coming back to our notes. I'm going to write a very basic definition here. What is DP? DP is recursion plus caching. If you add caching to your recursive solution, although it is not applicable on every single problem, it is only applicable for problems that have what do you call it, overlapping subproblems. That is, the caching has some use, right? Because if you cache something, you want to retrieve it again and again. So subproblems have to be overlapping. So if this is the condition, so dynamic programming is nothing but recursion plus caching. So if you want to look at the same problem again, from a dynamic programming perspective, okay, this might look, the solution may look slightly more complicated than your intuitive iterative solution, but just bear with me for some time. Suppose you wanted to compute the Fibonacci of 5. Okay. And we said, now this time, instead of evaluating this Fibonacci of 5, just pure recursively and then evaluating everything, why don't we keep a cache of the previously seen sequences? So let's say we keep an array with the indexes, let's say 0, 1, 2, 3, 4, and so on. And in this time we code looking at this array as well. So whenever we want to compute something, let's say Fibonacci of 5, we say return Fibonacci of 4 plus Fibonacci of 3. But before doing that, I check whether the Fibonacci of 5 is in our cache or not. If it is not in our cache, then it's okay. Let's go to Fibonacci of 4 and 3. Is Fibonacci 4 in our cache? No. So we expand it to 3 and 2. Then 2 goes to 2 and 1. And this 1 and 0. We know the base condition, so we initialize the last 2 numbers in our cache. So when we come to f of 2, we know the answer is going to be 1, and we store it in our cache. Similarly, when 3 comes, we store 2 in the cache. Now when we come to this 2, instead of computing it, we look at the cache here and get the answer back. So this is the dead end here. The tree doesn't move any forward. Similarly, when we come here, Fibonacci of 3, we look this place directly. We don't need to do anything. So you can understand how this works then. Essentially, what I do is, let me come back to the IDE. I'm going to modify this code a bit. Okay. Let me actually create a new file. And let's just call this fib underscore dp dot py. So in this case, there are multiple ways in which you can solve this problem. You can create a cache which is like a global variable, or you can create a cache which is passed to a function, or however you want. Let's just create a function. Okay, def of fib, and let's say it takes a number n. And let's assume that we have a global cache. Actually, no, let's keep it like this. Let's say we have Fibonacci of n. Now, we want to call this function the same way we called it last time. That is, we want to say Fibonacci of, let's say, 5 or Fibonacci of 8. So what we do is, this time when we call our Fibonacci function, then instead of doing this computation here, I'm going to call an auxiliary function somewhere else. Okay, and I'm going to call that function, let's say, def, let's say fib underscore dp. The fib underscore dp not only takes n, but it also takes an array, a cache of some sort, and we call this cache memo for now. And I'll explain why we usually call it memo shortly. Okay. So this memo is going to store the values of each items as we progress and calculate the Fibonacci sequence. So when we compute the Fibonacci of, let's say, number n, what we want to do is we want to first create an array which is completely initialized to 0. And the size of that array is len of n. Sorry, my mistake. N. Why len of n? N. Let's just keep it here. And there is a slight problem in this, but I will explain to you. And then what we do is we initialize the first 2 elements. Fib of 0 equals to 0, and memo of 1 equals to 1. So now, what have we done so far is, we want to compute the Fibonacci of 5, then we have created a memo of length 5, which is index 0, 1, 2, 3, 4. So in order to compute 5, we will need one more index here, 5, like that. So I will just add one more to this. So now we have an array of this, and all the items are initialized to 0. Okay, let's say the 0 is represented by this dot here. And then I'm calling my dynamic programming function with this memo. Now what my dynamic programming function can do is that it first of all can look at the base conditions, right? If n is equals to 0 or n equals 1, then essentially still nothing changes, just return 1. Sorry, just return n, my mistake. Else, remember the check that we were talking about. We want to check if this thing is present in our cache or not, right? So I'm going to check if the memo of n equals 0. If this memo of n equals 0, that means if this nth item is not computed yet, that is, it's still initialized to 0, then we want to calculate this as the Fibonacci of n minus 1 passing the memo in it, plus Fibonacci n minus 2 passing the memo in it, and slide Fibonacci underscore DP. Score DP and memo. So look at this call. It is exactly similar to this call. We are doing the fib of n equals to return n minus 1 plus n minus 2, but we are also doing this caching here. That is, instead of returning this answer, we are storing the value in a cache. And we are saying if that value of cache is not initialized, then call the recursion, but to fill the cache. And then essentially, once you're done, then just return the memo of n. Remember, the memo is n plus 1 length, so the n will be the last item here. Let's run this code. I'm just going to put a print and I'm going to run this code. What happened? Oh, shoot, I never called the function. So let me call fib underscore DP from here and pass n and memo to it. Let's run this code again. What's going on? What's going on? Did we miss something? Does anybody notice anything? If this item is 0, then basically the memo of n is n minus 1 memo and n minus 2 memo. 5 is, that looks correct to me. What is happening? Let's just run this code.
I'm curious about the syntax that you have on line 3.
Which one?
The line 3.
Right.
Yeah. What's the 0 in brackets there indicating?
So that's saying that initialize an array. This is an array with number 0, and the length is n plus 1.
Okay.
So it's pretty straightforward.
Okay, is that peculiar to Python 3?
What is that?
I'm not used to seeing that syntax to initialize an array, and most of my historical programming has been in Python 2. So is that a Python 3 construct?
No, this should be Python 2 as well.
Really?
Yeah, this should be similar. Yeah.
Okay. Well, I guess I learned something new. Thanks.
Yeah. But hang on, what is going on here? Why am I getting this? I'm just quickly gonna check something to understand what is going on. Print memo. Yeah, this is computing. What is going on? I'm doing something very silly, I think, somewhere.
I think your fib at the end should return something.
Oh.
Return, yeah.
Oh my God. I told you I'm doing something super silly somewhere. There you go. And that's the answer, 21 there. So let's get rid of it. And I'm printing, I think, somewhere else as well. So let's get rid of this guy. And let's run this. So 21. All right. So you can see we have computed it again this time. But this time, we are not calling recursion. I mean, we're calling recursion, but we are not recomputing results. But we check if this value is present or not. Now, this approach that we just saw, what is the time and space complexity? What is the time and space complexity both for this particular piece of code. Let's look at this. 5 evaluated 4 and 3, then 4 evaluated 3 and 2, then 3 evaluated, 2 and 1, and then this evaluated 1 and 0. We created an extra array of the size n plus 1. Then we evaluated 1, 0, we knew the answer, so we returned in one step. Then we evaluated 2 in one step. Followed by that, we evaluated 3 in one step because that's just a sum once again. And given 2 was already evaluated, 4 could be evaluated in just one step, which is 3 plus 2. Similarly, 5 could be evaluated in one step because 3 is already cached. So you can see the number of computations here are actually linear now. So now we are actually doing the linear number of computations. This is a dead end. This is a dead end. But we incorporated a cost of space by having this n plus 1 size of array here. So essentially, we got an O of n time compared to the roughly 2 to the power n time. And we got an O of n of space as well, in O of n of extra space we needed to do this. Now that does not count the space that's for this recursion. I mean, that's another n of space, so the complexity will remain n plus n is O of n still, but essentially, yeah, what we are talking is O of n extra space we need to compute this. This type of approach of solving a problem using this type of caching, although for this particular instance, this problem looks more complicated than the initial one, but at times this will reduce your effort a lot. But this type of approach where we begin from the larger size input and we call recursive function to smaller inputs till we reach a base condition and then we start filling cache, this approach is called the top-down approach. This approach is referred to as top-down approach. So usually when you do recursion, it will be a top-down approach. And this cache in the top-down approach is called, this concept of cache is called memoization. Memoization. So if you look up on Wikipedia or something, memoization essentially is just storing the results of the function calls of smaller size input so that later on when you're computing a bigger function, you don't have to compute the smaller functions. That's literally the meaning of memoization. So the top-down approach uses this type of a memoization. There is another way to solve this approach. There's another way of solving this, which is called bottom-up approach. And bottom-up approach, I guarantee everybody has done it already on Fibonacci sequence. And that is where the classical dynamic programming, that's when initially when the dynamic programming was brought into light, basically this was the approach that was designed. That if you want to solve a problem of size n, then you begin with the base condition. And then you incrementally build results. So for example, in this case, the base condition was 0 and 1. And then you incrementally build the solution for each successive step till you reach the n. So top down begins with this and recursively calls the smaller functions. The bottom up begins with the base condition and then moves towards the solution. And this tends to be recursive in nature. Well, everything recursive can be iterative. So essentially you can code it, but iterative as well. But I'm saying generally, this will be recursive and this will be iterative. So let me show you again, Fibonacci, an iterative solution. And I'm pretty sure everybody already knows about it. But in the iterative solution, what you do is you begin with, you write some kind of a loop, and you already know that what 0 is, what 1 is, and then you build the solution. So let me just once again code real quick. This should not take a lot of time. So I'm going to define Fibonacci again. I'm going to say n and return. I'm just going to copy. Actually, I'm just going to copy these two guys. There's nothing much to copy here. All right. So Igneous DP, you solve a problem using some kind of a tabular approach. The table can be one-dimensional, two-dimensional, three-dimensional. So in this case, the table is going to be one-dimensional and it's going to be an array. Okay, so I'm going to first of all create an array. Let's still call it a memo. And the memo is basically, I'm going to initialize it with 0 multiplied by n plus 1 again. Because f of 5 will be 0, 1, 2, 3, 4, 5. So 6 total elements. So n plus 1. Then I know that I'm going to initialize the 0 with 0 and memo of 1 with 1. Now I'm going to write a loop for all the numbers beginning from this index to last item. And I'm going to say for x in range 2, that is the index number 2, to n plus 1. All you have to do is the memo of x equals memo of x minus 1 plus memo of x minus 2. And in the end, just return memo of n, right? So no recursion, nothing. Each item, each index of the array is actually the sum of previous and previous minus 1. So previous and the second to previous. So let's run this code. And the answer is once again 5 and 21 as usual. So in this, we started the solution with 0 and 1, and then we built the solution from 2 all the way to n. And this is the bottom-up approach of doing the problem. The time complexity is still the same. The space complexity is also there, n. However, in this particular problem, we don't need a whole array. All we need is the previous two variables. So the whole creation of all the array is not really needed. And that's how you may have done in past as well. But I want to show you the aspect of DP here. So this is what you will do when constructing the solution from the ground up towards the solution. So any questions so far? Okay, so if no question, I'm still gonna just continue on this because I assume that everybody knows.
I actually have one question. I have one question. For the Fibonacci, the recursive one, if you swap n minus 1 and n minus 2, does anything change in your definition?
If I swap n minus 1 and
in the recursive version, yeah, like this is x minus 1, x minus 2. But yeah, if you swap this, even for the non, yeah,
like this,
yeah.
So let's look at it from this perspective. So what we are saying is, let's say you want to compute 5.
Yeah.
Then instead of computing 4 and 3, we're computing 3 and 4 like that, right?
Mm-hmm.
So how will this tree expand? 5 will call 3, then 3 will call 2, then 2 will call 1, essentially. And then you will have...
No, 3 call 1.
My mistake. Sorry, my mistake.
1 and...
3 will call 1, and 2, and this will not call anything, right? So you will have the answer to 1 and 0. So this is your cache. Assume this is your cache. So 0 and 1 is already there, right? Now it comes to 2. So for 2, we don't have an answer. So we do this 0 and 1. So that is already present. So 2 can be computed like that, right? Then you come to 3. Then 3 can be computed based on this previous information that we have, right? So the solution doesn't really change as far as I see, right? Because everything is coming from 0 and 1. So whether you expand 3 first or 4 first, you're going to go down to 0 and 1, then build it from there. Now, in order to compute 4, you will need 2 and 3. Both are already present, right? 2 and 3. So you get the answer for this 5. Is that the question?
Yeah. Thanks.
Cool. All right. So let's look at the example number 2. Okay, so example number 2 is also a simple example. Actually, it probably is not a simple example if you don't know about it already. It's a classical problem. And I will show you, I will first put the problem in front of you and then let you think for it for a few minutes. And then I'll discuss the solution for it. This problem is called maximum subarray sum. Maximum subarray sum. This maximum subarray problem. Hang on, let's put this and increase the font a bit. Let me copy this so that we can have a better look. What this problem says is, suppose you have an array of this type. Okay. Suppose you have an array of this type. You have to find a subarray which has the maximum sum. So, for example, just give me one more second. Let me copy this here. All right. So for example, this subarray here, the sum of this subarray is -1. Whereas the sum of this whole subarray is -2, -3, -5, -4. This subarray here, the sum is 3. This subarray, the sum here is 5. So you can think about all these subarrays that are present in this array, and what is the maximum amount of sum that you can obtain by having a subarray. Now, clearly, if this subarray all had positive numbers, right? 2, 1, 5, 0, 9, 6, like that, then what do you think the subarray would be? Can anybody tell me? If
Can
it
you
was
repeat the question?
Yes, it will be the full array, right? Because the whole thing is positive. Whatever you add is going to give you a larger number. But given that it has negative numbers in it, that makes the problem a little tricky. For example, in this case, the largest sum is going to be obtained by this subarray here. This subarray sums to 6. No other subarray will give you the better answer. Right, so clearly you can get the idea of how this problem is slightly tricky. Let's talk about the brute force first. Okay, if we were to solve this problem by brute force, then what we can do is we can generate all the possible subarrays that are present in this. all the possible subarrays. Like I can write something like a subarray routine, which will essentially generate all the possible subarrays. That will take O of n square, because I'll have to put two for loops, one inside the other. First, it will pivot on this and compute this, then this, then this, then this, then this, and all the way. Then I will pivot on here. Then I will compute rest. I will, include all the subarrays. So subarrays will be -2, then -2, 1, then -2, 1, -3, and similarly from 1, 1, -3, 1, -3, comma 4. So n square subarrays. And then I'll have to sum the numbers in those arrays as well to get them sum. So that will be another n. So for O of n square, n times sum will become O of n cube algorithm. That's the brute force approach of doing it. And you can do better. So what I want to give you is also this type of thing, that whenever this type of problem comes, where you have to find an optimal solution, a kind of a best solution when there are both positive and negative input present, then dynamic programming usually is a candidate. Just give me a second. Yeah. So dynamic programming usually is a candidate here. Let me show you how this problem can be solved intuitively. Okay, first I want to give you a few minutes. Maybe take like a couple of minutes. Think about how you will approach this problem if this was asked to you. And if you don't know the solution, then don't look at it at the moment. Okay, I hope you got some time to reflect on this. Now let's work on understanding this problem. This is a good pattern to understand because the thinking involved behind this will be pretty common in other problems as well. So let's take this problem. Assume that if you had an array with just one item in it. And I asked you what is the maximum subarray sum of this particular array. The answer is pretty straightforward then. The answer is 1. That is the item itself. This is a pretty simple base case, right? Now, suppose I had 2 items in the array. Okay, suppose -2 and 1. These 2 things. Then how would I compute the maximum subarray sum? There can be only 3 combinations, right? Either the first element or the second element or the sum of both the elements. Those are the 3 possible combinations in this case. So what we do, how we approach this type of problem is we go, once again, what we do is we create, let's say, some kind of a, let's go to the decision step first. We say, we look at the item number 0, okay? Let's say this is the item number 0. If we were only to consider this guy, the answer would be -2. That's the maximum you can obtain. Then we go to the next item. And here comes the decision point. Should I, at this point, extend the subarray that I had from here, or should I start a new subarray here? How can I decide which one of the 2 to pick? The decision can be based on either is going to be the max of either the previous plus current or current, right? If the sum of the 2 versus this element, whichever one is bigger, should be the start of the array again, right? So if my solution included just -2, then the answer would have been -2. But for the array of size 2, should I include the previous one or should I start a new solution from this point? I think I should start a new solution. Why? Because -2 plus 1 is -1, and this item is 1. It is bigger than the sum of these 2 items. Right? So I make this decision at this point of time. I don't need to compute all the subarrays and make the decision. In no case can this -2 be included in the solution if the sum of this item is bigger than the sum of these 2. Right? This -2 can only be involved if there was probably a 7 here. Then the sum of everything before this would have been better. Let's take that as an example. Suppose the, just give me a second. Just give me a second, guys. What's going on? Just give me a second. My computer's kind of hanging. Okay. Let's take another example. Suppose 7, -2, and 1. If we were to make the decision based on just this guy, then the answer would be 7. If we were to make decision based on this, let's keep this 3 to better understand this. Otherwise, there's no point. Yeah. 7. At this point, we decide what should we keep. Should we include this in the solution or should we not include this in the solution? If we include this in the solution, then the answer comes out to be 5. Otherwise, the answer, if we do not include, if we start a new solution from this point and exclude everything that's previous, then the answer comes out to be -2. Clearly, this is bigger of the 2, so we can discard this. Then comes to this point. Is the sum of the previous plus this element, which is 8, is bigger or this element is bigger? Clearly 8 is bigger, and hence let's keep this solution. And that's the total answer. That's the answer, 8 here, which is the answer. If you think 7 plus 3 is 10 minus 2 is 8. So this type of thinking will be needed again and again. This type of decision making at every step to see whether the previous whole solution should be discarded or should we keep it. So I'm going to go to this main problem here. Okay, and I'm going to call this, let's say, an array called local maxima, local underscore max. And it's an array of the same size. I'm going to start with the first element. I'm going to say first element. I have no option but to pick it. So I'm going to pick it. Then the next element. Should I start a new solution from here? That is, should I start a new subarray from here, or should I include this subarray as well? If I sum the two, then it's -1. But if I just keep this, then it's 1. That means starting a solution from here will always give me a better solution. So I'm just going to keep 1. Now, should I keep -3 or should I keep -3 plus 1? Like, should we have this two combined or just start a new solution from this? So -3 plus 1 is -2, which is better than -3. So I'm going to keep it. Now here, should I keep 4 or should I keep 4 minus 2? I should keep 4. 4 is a better solution. Now, come what may, and anything that's added before this, any subarray that starts before 4 cannot lead to a better answer, because this is the biggest sum to this point. And I move forward. Should I keep -1 or should I keep 4 minus 1, which is 3? I should keep 3. Should I keep 2 or should I keep 2 plus 3, which is 5? I should keep this. Should I keep 1 or should I keep 1 plus 5, which is 6? Should I keep -5 or should I keep 6? 6 minus 5, which is 1. I should keep 1 because 1 is bigger than -5. Now, should I keep 4 or should I keep 4 plus 1? 5. I should keep 5. What this is doing is, every time we discard the previous one, we say that if a solution was to start from here, nothing better can come from here. So in this array now, you can see the maximum sum is this guy, 6. And that is the answer for this. And I'm going to repeat this type of problem several times so you guys can understand what basically you guys become familiar with this type of thinking. Let's code this out. Okay, let's code this out. Well, first, before I code, any questions here in the explanation? Okay, let's code it. Just give me a second. Let me take, okay, 9. Okay, let's call the problem as max subarray sum dot py. Okay, I'm just gonna copy this array from here. Let's just copy this guy. And this will be problematic actually. So let me just. Sometimes these minus are not minus, but they're dash. So I'm gonna make sure that. Let's say that this array equals to this. And let's just print array once because I want to make sure there's no formatting problem. Okay, yeah, this is good. Now let's do the max subarray problem on this. I'm going to define a function called max subarray sum. And it takes an array as input. And here I'm going to say max underscore subarray sum of array. We can put this anywhere I want. Now, the first thing that we're going to do in this solution is we're going to create a local maxima kind of an array that we're going to build. Right? So the local maxima array, let's just call it local max. And the local max essentially is an array of, let's just initialize it with 0 again. And 0 multiplied by len of array. So we are going to create an array. Each item is 0, and the length of that array is this array. So local max is this. Right. Now we are going to initialize the first element, because that's the base condition. We just the very first item to the array of this item. Right. So let's go back here. Very first item. The only option is that the local maxima is going to be this much, nothing else. So if this is the graph, then this begins at -2. With the addition of 1, this goes to, then we stop here and then we take 1. Then -3, like that. And basically then 4, 3, 5, 6, 1, 5, like that. And this comes out to be the top element. Now, let's initialize it. Now I'm just going to go through this whole array. Okay, let's just say for x in range of 1, because array of 0 is already initialized, to len of array. Okay, so I'm going to go from all the items from here to the end, and at each item I have a decision to make. And what is that decision? Either I'm going to pick this item or this item plus the sum of the previous local maxima. So I'm going to say either this item, which is the array of x, or the array of x plus local maxima of x minus 1. Whatever is the maximum of that. Whichever one is maximum, we're going to pick that element, and we're going to assign this to the local underscore max of x. So essentially I'm saying that, let's say I'm on this particular item, then this item either is equals to this or this plus this, one of the two, whichever one is maximum. And the rationale behind this is that whatever one is the maximum will yield to the maximum result. There is no way other item can give me better result. And then once this all is computed, let's print. Okay, let's just say local underscore max. Let's just print it. When you run this code, you will notice that this is the local maxima being printed. And then what we can do is we can just return the max of that local maxima. Return max of that local underscore max. So what I want to focus on this particular problem is that decision making. And this we will see several times when we computing cost of different type of problems. That should I take this item or should I include the previous result plus this item? That should I begin a new answer with just this item and then going forward, or should I pick everything else plus this item? That decision is important. And I encourage you to go and check this. I have solved this using an array, but an array is not really needed. If you look at this solution, all it needs is two variables, the local maxima and the global maxima. At each step, you compute the local maxima, and then you based on that, you compute the global maxima for that step. Because at each step, all I need to look at the x minus 1. I'm not concerned with this. So if I just keep the previous state, I will be able to generate the right answer in the end. Any questions? Okay, if there are no questions, I assume that silence means no questions. Okay, then I'm going to stop the recording. And that's it for this session.